Hello everyone. Today we are moving on to the chapter 5, talking about the link analysis. Since the development of the internet and the social networks, we have facing a lot of data organized in graph forms. So the link analysis and especially with the PageRank have become a very tremendous manner to talking about. As we can recall from this image, the graph data occupies a very important analysis area in the data mining. It will involve the PageRank and also including an advantage version about the SIMRank. And also the graph data analysis can also be used in the community detection and also together with span detections. Here is a graph data drawn obviously from the social networks, and we know its shapes more like the continental Earth. So this is from the Facebook. Okay, so we from this image we know that the social networks are covering everywhere in the global Earth. This image shows that the connections between the political blocks, which is a demonstration regarding the polarization of the network in 2005. Obviously, we can identify the red is for one side and the blue is for the other side. And actually, all the yellow part are kind of some people in the middle swinging between the yellow or red. This image is drawn from the journals, to describe the relationships between these different disciplinaries regarding the science citation. We notice that in the green part is biology. Obviously, it has some connections with biotechnology and especially with the chemistry and civil engineering as well. And the social science, which actually is orange part, has some connections with brain research and a few junctions with the humanities. Okay. So where are we? The computer science and engineering. We notice that the pink cluster here is regarding the computer science and electrical and electricities. Okay, so this so from these graphs we know that the connections and especially the networks are everywhere in every aspect. Especially as we know from the internet itself is a kind of communication network composing from the trunk, composing the backbones, and all the endpoints are composed with different PC and laptops. This is a very famous problem or changes regarding the 7 bridges in Königsberg, which proposed by Euler by 1735. This is a very famous question. Although graph questions, although we already know the resolution of these questions. So as we know, the web is as a graph. It can also be viewed as a directed graph. For example, the nodes in the web indicate the web pages, and all the edges direct to the hyperlinks. Okay. So this is a typical directed graph as we can illustrate in this image. For example, this is a kind of university, and we have a class, and we are running a network, and also I teach in the uni, and probably the network has some blog for the post and the evaluation regarding this class. Also, the blogs may have connections with some news and other colleagues and social networks. Okay. So here is a very broad question regarding how to organize the web. In other words, how the web is organized. It is easy to answer this question. Human created directories, the web directories. So the directories, so that every page is categorized following these directories, just like the libraries do. And the second try is about the web search, which are most relevant with the information retrieval, which investigate how can we find the relevant document in a small and trusted data sets. For example, we need some available and readable newspaper articles and some worthy patents, etc. But the changes is that the web is huge, full of actually most of the web are untrusted documents, random things, and even web spams. We try to redirect or even misleading the people for their own purposes. Okay. So here is the two challenges regarding the web search. The first one is that since the web contains many sources of information, who to trust? The trick is that trustworthy pages may point to each other, right? Okay, but still, how can we find at least one trustworthy page? The second challenge is that what is the best answer to query with the keyword newspaper? There probably not a single right answer for this question. The proper trick is that probably is that the pages are actually know about the newspaper, might be pointing to many other newspapers. So we probably understand that the newspapers are pointing to each other. They more likely to form their own information circles. Okay. So all the two challenges will be finally conclude in the ranking. How can we ranking the nodes in the web graph, and how can we indicate which nodes are important? As we know that not every page are similarly or equally important. For example, the link here, www.joeschmo.com versus www.stanford.edu, which is more important or more prestigious to the students? Obviously, the later one is. So since there is a large diversity in the web graph node connectivity, so we are trying to find a method to ranking the nodes according to their to the link structures. So actually, from this image, we probably I would give you a question: which node is more important, the red one or the blue one? The answer I may not reveal this moment, but I believe all of you may have your own feelings and thoughts. Okay, so let's move on to the concrete algorithm. How can we find the important nodes in the graph, whatever the graph is? So here are a couple algorithms we are going to discuss step by step. The first is the PageRank. The second is the topic specific, or sometimes called a personalized PageRank. The third is the web spam detection algorithm. As we know, web spam are always pervasively in the web, which are running and try to redirect and misleading for the for any kind of bad purposes. Now, PageRank. So first, we need to think about where the PageRank are coming from. So as we know, one of the biggest changes in our lives in the decades following the turn of the centuries, which was the ability of efficient and accurate web search. Since the search engines are coming out, there are always some people trying to using the spam to misleading the search engine. As Google is not the first search engine, but it's the most successful search engine, as it can fight or defeat the spammers who has made other search engines most useless. Moreover, the innovation provided by Google is a non-trivial technological advance called PageRank. This algorithm give us how to identify the useful information and some unuseful information with a very strict algorithms. Okay. So the PageRank, the main idea of the PageRank is that this algorithm will using the links between the web pages as votes. So as to that, once a page receives more links from others, so it will get more links. Probably one thing we'll think about how can you see about the receiving? But when I'm using the receiving, not giving out, has indicated my purposes. Okay, since we know the links are two directions, one is incoming links, the other is out links. So we are using the incoming links as a vote. For example, the Stanford.edu receives more than 23,000 in links, while the joeschmo.com received one incoming links. So the answer is very obviously. And even a website receives the links from many other nodes. The links are different. Between all the incoming links. So why? So we always have the experience that the speech from some powerful people are more influential and persuasive rather than normal people. Okay, so this is the philosophy behind the differences of incoming links. Okay, so from this image illustrating the PageRank scores, we probably understand the B and C, actually they are most influential nodes in this graph, while the node A, D, E, F are kind of have not so much influential. Okay. So before we discussing how the numbers or scores in each node coming from, we will discuss the simple recursive formulation first, right? In this formulation, we notice that we give the precondition that each link's vote is proportional to the importance of its source page. So this link refers to the incoming links. For example, if page J with the importance of indicated with RJ has n outlinks, so each link will have evenly spread RJ divided by n votes. So the page J's n importance is the sum of the votes on its incoming links. So in that case, page J can give out importance to other nodes or pages. Well, it can its own importance is the number and weight of the links it receives. So from this image, we notice that the RJ, the weight of RJ actually is calculated based on the incoming links from the node I and node K, because J gave out the links to the other blue nodes, and only incoming links from I and J. So since the I has 3, 1, 2, 3 outlinks, so the weight of Ri is divided by 3. So the same discipline applies to the K, as K got 4 outlinks here and 1 incoming link. So the weight K has been evenly spread out on the 4 outlinks. So this is how the J weighted according to its incoming links. So based on the simple recursive formulation, now we can have this following definition here. The PageRank is a kind of flow model which indicate the links flow between nodes. So in that case, a vote from an important page is well worth much more than a normal page, much more than normal page. And also in the meantime, if a page it has receives incoming links from unimportant pages, so this page becoming important as well. So in that case, the ranking for formulation can be normalized in this formula. And also in any graph here, we can construct a set of flow equations here. For example, for the node Y, so Ry have 2 outlinks, and actually it has a self-link, so it also take into consideration. So Ry receives half of its weight, and also half of the weight from A. and A give out two outlinks to M and Y. So Y has half of the RA. Based on the last slides, we got a set of equations. In this set equations, we got three unknowns and no constant. So in that case, there is no unique solutions. So we probably we need to have an additional constraints to forces the uniqueness. For example, we can assign all the weight, all the importance and weights of all nodes equals to 1. So in that case, we can get the solution of the assignment of each node on this graph, so that we got Ry, Ra, and Rm. Okay. So as we know, this is a solution for the equation set. We probably know that understand the Gaussian elimination method will work for the small examples, but also we probably need a better method for large website graph. As we know, as the graph becoming bigger and bigger, the equation sets will be unpredictable huge. So probably we are requiring a new formulation methods to sort out such equation sets. Now we introduce the matrix, the stochastic agency matrix for this solution. Suppose we have page I has di outlinks. For example, from di to j. So we're using the mji indicate the links from I to j, which has evenly spread of the weight of I. So mji equals to 1 divided by di. Otherwise, the ji is 0. So in that case, the M is called a colon stochastic matrix, which means that all the matrix in the colon will be sum up equals to 1. In the meantime, we will introduce the rank vectors R. The vector with an entry per page. The Ri is the importance score of page I. So in other words, all the sigma with under a script I equals to 1. So in that case, the flow equation can be written as R equals to M times R. If we illustrate this formulation here, we are supposing the Rm times R equals to R here. If we recall the matrix series, we suppose that each page I links to 3 pages, including J. They will have such flow equations here. So the question is, how can we solve this formulation? Since we already construct such a formulation with the introduction of the stochastic adjacency matrix M and the vector R, so how can we solve this formulation so as to obtain each weight for each node? So in that case, with the matrix series, we can know that the rank vector is an eigenvector of the stochastic Y matrix M. So this is a conclusion we get from the matrix series. In fact, it's the R is the first or principal eigenvectors with corresponding with the eigenvalue 1. So in that case, the largest eigenvalue of M is 1, since M is colon stochastic with non-negative entries. So now we are trying to find an efficient way to solve for vector R. Okay. So the method we can recall is called power iteration. Shall we look at this a simple example with the power iteration here? This is the previous an example. We get the formulation here, and also when we introduce the adjacency matrix and the vectors, we can involve this matrix formulation at here. Okay, that's the M we got from this adjacency matrix. Okay. Now, how can we solve this formulation? We already done in the Gaussian elimination, but how can we do the find the solution with the power iteration method? So, given a web graph, for example, with n nodes, where the nodes are pages and edges are the hyperlinks, the power iteration is a very simple iterative scheme. Suppose there are n web pages, so the initial the weight of each node will be initialized with equal weights. So in that case, the R 0 for the round 0 before any computation will be 1 divided by n for these vectors. So how can we iterate? We are using the R equals to matrix M times multiplied with RT. So this is the iteration strategies. When shall we find the final results? We know the contingency once we know there is quite a smaller epsilon here. We will stop, which means that there is no big change between this between the result of this round and the last round. So so the convergence is much smaller than the expectation. So this is the stop standard, which is much very widely applied in this computation with machine. Okay, so now how is this iteration really works on this example? Okay, based on the previous assumptions, in the round 0, all the R's are assigned with equally average number. So it's a 1/3 here. And after a couple iterations, we can notice the changes here. In the round 1, in the R1, we got 1 divided by 3, 3 divided by 6, and 1/6, and whatsoever. And after a couple iterations, finally there is no more changes between the round 1 before the round t plus 1 and the round t. So the final result is like this. This is the same computation result as the Gaussian elimination solutions. So why is the power iteration working? So the power iteration indicates a method to find the dominant eigenvectors corresponding to the largest eigenvalue. We can this process can be illustrated in the following formulation here. R1 equals to m times R0 and R3 equals to m times R2. So we will get the consequences after a few rounds of the to find the dominant eigenvectors of m. So if we claim the sequence of m, we need to prove that this will present the dominant eigenvector of value m. So the proof procedure is that if we assume m has n linearly independent eigenvectors, so for example x1, x2, and xn represent the corresponding eigenvalues. Well, lambda 1 and lambda 2, we can assume lambda 1 is bigger than lambda 2 and then lambda n is the smallest. So in that case, the vectors of xi corresponding we can be written like this formula here, and well, the MR0 can be represented in this formulation here. So if we repeat the above multiplication on both sides, well, produces this formulation here. So if we go on to simplify this formulation, if we replace the rewrite this formulation, we can have this simplified results here. So in that case, we will know that the MK R0 are approximately equal to C1 and lambda 1 and K xi. So therefore, once the C1 equals to 0, so the method won't convergence, which is should be avoided from these scenarios. Okay, so this is how the power iteration works. Next, we can using the random walk for the this interpretation. Imagine a random web server which at any time t server is at one page. At time t plus 1, the server will allow an outlink from I either to I1, I2, or I3. So as we assumed before, all the Ri will be sum up equal to the Rj. So let's pt as a vector whose ith coordinate is the probability that indicates the server will go from the page I at the time t. So pt is the probability distribution over pages. Okay. So in that case, the pt can be written in this formulation like p, the probability at a time t plus 1 equals to the matrix multiplied with probability at time t. Suppose the random walk reaches the state, reaches the maybe constant state. Finally, the p probability at the times t plus 1 will equal to the probability at the last in the last round. So in that case, we will reach the stationary distribution after a random walk. So as our original ranking vectors satisfies this formulation, so we can conclude that the R is the stationary distribution for the random walk that we are looking for. So the as the existence and uniqueness regarding this results of this solution, the central result from this theory of random walk, which also as known as the Markov processes. So once the graph that satisfies certain conditions, the stationary distribution is always unique and will eventually be reached no matter the initial probability distribution is at the time when time t equals to 0. Now we shall look at the PageRank in the Google's formulation. So the PageRank actually arises 3 questions. Whether this formulation will finally converge. Does it converge to where or what we want? And is the results reasonable? So the first question is, does this converge? So this obviously is an unconverged example here. So this is unconverged example. Because finally it will reach to, we can compare the iteration is different from the last iteration. Okay, so as a PageRank, we are trying to find the potential threats to this solution. The PageRank is facing 2 challenges. The first one is called dead ends, which means that there is no outlinks once the random walk will go to one end while never coming out. The other is the spider traps, which is indicated with the green nodes here, which means that all outlinks are within a group, so the random walks will get stuck in this trap and never get out. So actually the spider traps will absorb all the importance in this circle. So in that case, will cost very unevenly assignment about this weight. So here is an example how can we demonstrate the spider trap with these formulation computations here. Suppose we have R, Y, YAM, we have this formulation, and with the initialized values, after a couple iterations, finally the RM, which actually absorbed all the importance, will actually reach the 1. Some students may argue why the node Y is not a trap, because Y has an output from Y to A. So although Y have a self loop here, Y still is not a spider trap, while M receives the outlink from A and never coming out with its own self circles. So based on this condition, we need a solution to overcome this trap. So the solution is the teleports. The teleports is very simple. Is that at each time step, the random surfer has 2 options. Once it has detecting the existence of the spider trap. So with the probability beta, we will follow a link at a random, while the probability of 1 minus beta will jump to another random page. So that's the common value for the beta are in the range from 0.8 to 0.9. So there's still about 10 to 20% chance that the spider can jump out of the trap just within a few time steps. Okay, so this is kind of optimization regarding the solution to the spider trap. Okay, as we mentioned before, there is another problem, the dead end. The dead end is fairly easy to identify from image here, as M receives the outlink from A and never have an outlink, even a self-link here. So if we apply the iteration from round 0 and round 2 and round 3, we will finally notice that all the nodes will receive zeros at this moment. This is obviously not revisional according to our solutions. Okay, so interestingly, the solution to this problem is still the teleport. So the policy is different, that once the random teleport will link with the probability from dead end, which means that once the dead end is identified, it will have the 100% probability to jump. It must jump to overcome this dead end. So why teleport solves these problems? Especially the dead ends and the spider traps are solved in one policy, because the spider traps is not really a problem at all. But with traps, PageRank scores are not what we want. So we never should get stuck in the spider trap by teleporting out of its infinite number of loops rather than finite number of steps. Dead end is really a problem. It will never give out a result, so the matrix is not colon stochastic, so our initial assumptions are not met. So the solution will make the matrix column more stochastic by always teleporting to nowhere and else to go. So the random teleport can be formulated in this formulation in Google's solutions. And so this is the PageRank equation, and the beta has been and one minus beta has been added here to overcome the spider trap and the dead end in the PageRank equations. So here is the PageRank equation, which has been reformed in the practical production online. So as we mentioned, the beta is generally 0.8 and 0.9. If on 0.8, which means that every 5 steps there is always a jump will happen here. So if we apply the beta of equals to 0.8 to using these iterations, we can solve this spider trap. We will get that the YAM will finally reach a convergence result like this. So now, how do we actually compute the PageRank according to the Google's formulation? The computing process will be like this. The key step is the matrix vector multiplication. We construct this formulation. So easy if we have enough memory to hold. say if we got more than 1 billion pages, we probably will need 4 bytes for each country, for each entry, and about 2 billion entries for vectors. That requires approximately 8 gigabytes. So the matrix A should have n square entries. So in that case, the 10 with power 18 is really a large number to compute. So in that case, we are using the metric formulation. Suppose the n pages. Consider page I with di outlinks. We still assign the mij equivalently in the initialization stage. So the random teleport is equivalent to adding the teleport link with the probability of data. Okay. So this equation can be rearranged like this. We got R equals to A multiply with R, well, A take this including the probability of teleport, and including the adjacency matrix M here. So we are using the A to like an optimization results of the beta M at this moment. So after rearranging this formulation, we get this formulation here. Okay. So still we can using we know that the M is a sparse matrix. So probably that 10 links per node, that is roughly about 10 times n entries. So we can using for each iteration, we only need to compute the R new equals to beta M times R old. In that case, we added a constant value of 1 minus beta divided by n for each entry. And if the R new sigma sum up is more than 1, we can renormalize the R new to what's it sum up to 1. Okay. So the complete algorithm of PageRank can be stated as the pseudocode here. As we know that we set up the R old like equivalent values, and we repeat all these steps until we get a final convergence of the epsilon. Okay. As to the sparse matrix, we have another method for matrix encoding here. The basic algorithm we can use the update step for the power iteration, and we can construct still using the iteration to assume to using the RAM to update in the memory, and the update algorithm is based on the block, on data block to update in the memory as well. Why the block update is efficient? Because it's similar to the nested loop join in databases. So the R new is breaking into K blocks so as to fit in the memory, and M and R old once for each block. So the total cost will be the K scans M and R old. So the cost per iteration of the power strat will be like in this formulation here. So there is a probability that we can achieve better results. For example, M still much bigger than R, so we can avoid reading M K times per iteration. So is that we can read the block strip. We can further divide the block into different strips, one step by step, to reduce the reading cost, to the reading cost to the memory. So still we will find the convergence using the cost based on the cost per iteration and the power results here. So as far as we so far as we can conclude for the PageRank at this stage, we know that the PageRank actually measures generic popularity of a page based on, but not against on the topic-specific authorities. So this issue will be solved out by the topic-specific PageRank in the next lecture, and also the PageRank using a single measure of importance. There are also other models of importance. So the solution is that hubs and authorities are also taken into consideration of this PageRank algorithm in the next lecture as well. And also the PageRank is still susceptible to link span, which are very easily affected by the artificial links topologies to created in order to boost an artificial PageRank. So the PageRank will be optimized to defeat the link span with a new version called TrustRank. So it's good for today's lecture. So see you in the next part. Okay, thank you everyone.